Today let's talk about Codeforce 2023 problem C. First part is description. You are given two graphs. They are not same. There are some information about the two graphs. First of all, the age of the graph is directly. That means there is a direction for every edge on the two graphs. Secondly, it's strongly connected. That means you can go to any node from any node. It is acceptable. Thirdly, this is the most important for every circle. For every circle in the two graphs, length is divisible by k. That means the length of every circle on the two graphs is divisible by k. This is the some information about the two graphs. In addition, we will add a tag for every node on the two graphs. The tag can be ingoing node. Type of the node. First is ingoing. Second is outgoing node. That means the problem is that means the node will be ingoing node or outgoing node. The problem is after we can add n edges between the two graphs. After that, we need to promise every circle the length of. After that, we will get a whole large graph, and we need to promise the length of every circle in the big graph is divisible by k. This is what we need. For the ingoing or outgoing nodes, ingoing means it can be the endpoint of edge. For outgoing, in contrast, it only can be the start point of edge. This is the strategy. This is the limitation of the node. For example, if this node is ingoing, that means we only can add an edge from graph 1 to graph 2. We cannot actually, in contrast, we only can add an edge from graph 2 to graph 1. We cannot make the contrary direction edge. So what we need to do is to determine if there is a strategy we can add n edges between graph 1 and graph 2. After that, the whole graph can promise that every circle of it is divisible by k. This is the description part of this problem. Next part, let's talk about solution. For this part, the most important is to have a deep understanding about the information the problem provide. That means we need to have a deeper understanding about the third information. That means every circle length is divisible by k. That means modulus k equals 0. Let me take an example. This graph, k equal 5. Let's take this as an example. Actually, if for every circle length is divisible by k, there are two circles on this graph. This is the first circle, and the large circle is the second one. So actually we can take it smaller. This is a large one. Okay. Actually we can, if this information is correct, we can paint a color on every node on the graph. For example, that will be the first graph, the color will be 0, second is 1, this will be 2. That means for every edge we want to make the color of end equal color of star plus 1 modulus k. Actually, these two information are equal. These two information are equal. We can check. We can take this example to check. If this is 1, 0, 1, 2, and this will be 3. And after 3 plus 1, modulus k will be 0, because actually k is not 5, k will be 4. So this is 1, this will be 2, because there are this edge. This will be 3, this will be 0, this will be 1, and it meet the requirement that ends equal star plus 1 modulus k. So we need to, the important information that we need to understand to solve this problem is these two information are equal. For every circle, the length of the circle is divisible by k. There is another way to express this information. That means for every edge, we can paint the color, and the color of the end point of the edge equals star plus 1, and modulus k. These are equal information. So for this problem, we will know for the two graph. For the two graph, we will know we can paint color to any node on the two graphs. C1, C2, C3, da da da. So this is graph 1, this is graph 2. After that, the target is after we add n edges to the two graphs. For the whole graph, we need to promise the circle, the length of any circle in the new whole graph is divisible by k. That is equal with, for the new whole graph, we need to promise every edge is every edge can meet the requirement end equal start plus 1 modulus k. That means if we, for the every edge we add to between the two graphs, the end, it can promise the end equal start plus 1 modulus k. After that, it is obvious the length of every circle of the new whole graph will be divisible by k. So what we need to do is to promise the new edge can meet this requirement. So this will be a simple question, because for this graph, if the color of this node is C2, we can match this node to C2 plus 1. In addition, if this is a outgoing node, so we can add this edge from the C2 to C2 plus 1. In addition, if this is the color of this node is C3, and this is a ingoing ingoing tap node, so we can add a edge from the C3 minus 1 to C3. So this is the requirement when we add a new edge between the two graphs. This is what we need to do. But there are lots of nodes on the two graphs. So in addition, we can rotate. That means we can rotate the color of the node. After we rotate it, it is also can meet the requirement. So maybe this is the one. So after we rotate it, if it can match the requirement, it is also accepted. So we need to process the rotate situation. For this situation, we can make up two arrays. This is the next step. We can make two arrays, count 1 and count 2 for the two graphs. For the count 1, for every array, the key of it is the color of the node, and the value will be numbers, amount of nodes with color. Okay. So that means what we need to do is shift several positions for the count 2. That means make a rotate for the graph 2. After we shift position for count 2, we can make the count 1 equal count 2. This is accepted for the problem. There is another solution for that. That means we can concat two same count 2. That means this is count 2, this is also count 2. We can get a new count 2. We can check if the count 1 is a sub-array of count 2. If count 1 is a sub-array of new count 2, that means after we shift several positions for the count 2, and the count 2 will be exactly the same with count 1. For example, this can be the count 1. So that means after we rotate several shifts about graph 2, after we do the rotate, we can make every node in the graph 1 to match the node on graph 2. Okay. This is we can use the KMP algorithm to solve this problem. I will not provide more detail about KMP algorithm in this video. In addition, let's talk about the next problem to totally solve this problem. In the next step, there is only one issue to totally solve the problem. That means if we for the ingoing and outgoing, for the ingoing node set and outgoing node set in the graph 2, the shift position is not the same, because for the same color in graph 1, for the ingoing node in the graph 2, the shift position will be C2 plus 1. That means the important part is plus 1. But for the C3, the outgoing node on the graph 2 should be -1. That means the shift position for ingoing node set and outgoing node set will be some difference. Actually, the difference of shift position that it also can call shift distance will be 2 because there is +1 and there is -1. So if we shift the ingoing node on graph 2, we also need to shift the outgoing node in graph 2. So the shift position must be the difference between them must be 2 because one of them is +1, one of them is -1. So this is the all requirements we need to meet to return yes. That means after we add n8, there is a strategy when after we add n8 between graph 1 and graph 2, the length of every circle in the new graph will be divisible by k. Okay, this is the all solution part for this problem. If there is any confusion, welcome to submit your problem below this video as a comment. Okay, last part will be complexity. For this part, actually, what algorithm we use for the term complexity? We don't use much complex algorithm. The only algorithm we use is KMP. Other will be logical thinking issue, like count the amount of nodes with color key. So the time complexity will be O(n). For the space complexity, we don't need extra space to store variable. So the space complexity is also O(n). Okay, this is a complex problem. If you have any confusion, welcome to submit comment. Thank you for watching.